Hey there everyone, welcome back. In this video, we're going to talk about work in relation to the spring force and springs. We haven't talked about springs yet in this class, right? Whoops. So I'm sure you're all aware of what a spring is, right? And how they come in various sizes and stiffnesses, right? You can have a very small, a weak spring in something like a pen cap, right? Or you can have very stiff springs, very thick, very strong springs in something like your car's suspension system, right? You have four springs essentially that the car chassis sits on, and so those springs are very, very stiff. And so what's known as the spring constant value is very large. So what I have on the left here is three images of a spring system. So we have a horizontal surface with this box that's attached to a spring, and the spring is attached to a fixed wall, all right? And so this block is free to move. There's no friction on this surface. And initially, if the spring is unstretched and uncompressed, right, it's just relaxed, it's at its natural length, then we can call that the equilibrium position for the system. Okay, there's no force from that spring on that block, so we call that x0. On picture B, some external force, in this case a hand, comes along and pulls the block to the right, and in so doing, it makes that spring create a force that pulls the block, that tries to pull the block back to the left. So we see the spring force here always wants to pull that object back towards equilibrium, right, if it's displaced. So the displacement is to the right, spring force is to the left. They're in opposite directions. In the last picture, it's the opposite, right? The spring is compressed, so the displacement is leftward, but the spring wants to push the block back towards its equilibrium position. So again, it's still opposite. So in picture B, the displacement's positive, spring force is negative. In picture C, the displacement is negative, the spring force is positive. So let's take a look at the work done by the spring, and then we'll look at the energy that the spring has, right? The potential energy that the spring has in order to speed up this block, right? Or accelerate it, if you will. So first, the spring force, which we'll call F with a subscript S, that has the form of negative K times some displacement. And so since this is in the x direction only, I'll call that displacement x vector. So that K, that variable K, is the spring constant. And this is characteristic of a spring, right? All springs have their own characteristic constant value, right? You can think of this as the stiffness of a spring. So the spring inside a pen cap has a very low value for K. The springs inside your car's shocks have a very large value, okay? So another thing to notice is that the negative there means that the displacement and the spring force are opposite, okay? Usually. I'll say usually. So what we'll do is that we'll calculate the work done by the spring for several different cases, right? What is shown here is just two different ones. Let's take a look at when you release this block, right? Starting from this position, when you release it, what's it going to do? It's going to be pulled to the left and accelerate to the left, right? But once that block passes the equilibrium position, now it's over here. Well, now it's compressing the spring. And so it's like down here. Now, it may still be moving leftward, but there's a spring force to the right, right? As it's slowing down to a stop, right? A maximum compression distance. After that, the spring wants to push it back towards equilibrium. So the displacement is right and the force would be right. So before I get into those 4 cases, let's just take a look at the first one, okay? So B, whoops. So in this case here, if some person were to come along, grab that object and pull it to the right, what's the work done by the spring? Not by the person's hand, but by the spring. So as it's moving from equilibrium, so say point A to point B, the spring force, the work always has the expression integral from A to B of some force, in this case the spring force, dotted with some displacement. In this case I'll say it's dx. Okay? That's always the work. So let's put in the spring force. It has the magnitude, or rather the expression of negative kx. So let me pull the k outside the integral. A to b. Now we have the x vector dotted with the dx vector. All right. Now it's time to evaluate the magnitude of that dot product. All right. So the magnitude of x vector is, well, x. Right? That's over here as the maximum displacement distance. What direction is that in? Well, x hat. You can, yes, also use I hat if you want to. And that's dotted with the magnitude of dx. Well, that's, dx. And that direction is also x hat. Okay? And so now we have the magnitude of both. Evaluating the dot product, we have negative k, integral a to b, is x dx. And we have x hat dotted with x hat. Cosine of that is 1 because they're in the same direction. All right? And so now, evaluating the integral, we have negative k x squared over 2. I'm going to pull the 1/2 out and say x at the final position squared minus x at the initial position squared. All right? And so we can write this as, well, the change, or rather the negative spring constant over 2 times the change in position squared. In this case, all right, in most cases, one of the positions, final or initial, will be 0. Right? So one of these may cancel out and make our lives a little bit easier. So in the first case, we have it starts at 0, and then it increases or is stretched to maximum position x. So final minus initial. A is the initial position, so that is 0. And it turns out that the work done by the spring is negative 1/2 k x squared. I dropped the b because it's just simply the maximum x value. Look here, the work done by the spring is negative. Again, because the displacement and the force are in opposite directions, so that does a negative work. You'll also remember from previous videos that work is equal to negative delta U. Right? And so this means that the spring has a positive potential energy because the negatives cancel out. And the magnitude is 1/2 kx squared. So the spring, as it's being stretched from equilibrium out to some maximum distance, does a negative amount of work. Well, that means, in other words, that its potential energy is increasing. Okay? So now let's take a look at the other instances. I'm going to do it like this. So if that's x equals 0, we have case number 1. We said the box was out here, so there was a force that direction and a displacement that direction, x. So we said the work done by the spring is negative 1/2 kx squared, and that's equal to a negative delta U. Again, that comes from the fact that work is equal to negative change in potential energy. And that means if you have a negative out here, that means, well, the final potential energy, right? This is delta means final minus initial. That means that the initial is less than the final. Am I saying that right? No, the final amount is less than the initial amount. Okay? You might also remember that work is positive delta K, right? So now that it has some initial potential energy, right? So this was the U initial, this was U final. Now in position 2, it accelerates to the left back towards equilibrium. And so in that time, there's a force on it, that direction, and a displacement in the same direction, right? It's being pulled, it's being accelerated back towards equilibrium. And so we have both the force and the displacement are in the same direction now. So we will get a positive work value. The spring does a positive work, right? It accelerates that object because it pulls in the direction that it's moving. Well, work is always equal to negative U. Now it means that the potential energy change is decreasing. All right, so let me write that like this. Delta U is now a negative 1/2 K x squared. Okay? This means that the U final is 0 and U initial was some value, right? So now the final amount of energy is less than what it started with. That can only happen if the object speeds up. So the kinetic energy is increasing as the potential energy is decreasing. So let me put it that way. Then we have a positive, delta K is positive. Let me just write it like this. Okay, it speeds up, in other words. And now in case 3, or segment 3 rather, over here, it passes the equilibrium point and slows down to a stop at some maximum displacement, but on the left side, right, in the negative direction. So now, as it goes from the initial point to the final point, there's a force wanting to pull it back towards equilibrium, slowing it down, force, and the displacement, though, is still left, right? It's still moving left, but there's a force right. So that's why it slows down to a stop. And in this case, the work done by the spring is like it was in position 1. They're in opposite directions, so we get a negative work value. Again, the delta U, though, is positive. Right? The final potential energy is greater than the initial potential energy. So we get a positive value here, like we do. And that means that it slows down to a stop. So kinetic energy is decreasing. I can actually write that. Let me jot that down. Delta K is negative. Right? It should be noted that in this case and this case, that there is no other external force, right? Initially, the hand pulled the object back this way, and then it released it, right? So the object here was only under the force of the spring for that part and that part, okay? And so in segment 4, still on the right side, but now it will be moving back towards the right from the far left to 0 again, right? So now there's a force pulling it to the right, and it's also moving to the right. And in that case, as in, I guess, section 2, we have a positive work done. Whoops. And as always, work is equal to negative potential energy, right? Negative change in potential energy. So that means that delta U is negative. In other words, it went from some maximum displacement over here down to a displacement of 0. So the potential energy is decreasing, thus it's speeding up. If the potential energy decreases, the kinetic energy has to increase. So once again, it speeds up. And so this is one complete cycle, right? Over here, back here, and then back to equilibrium. This entire cycle will continue over and over and over again, and if there's no friction, it'll continue infinitely. If there is friction, eventually it'll, go like this and this and this and this and then pretty much stop, right? But this is the process here, right? Every time you have the force and the displacement in opposite directions, that force is doing negative work, which means that the potential energy is increasing. I didn't write that here. Delta U is positive. If the potential energy is increasing, the kinetic energy must be decreasing, which means it must be slowing down, okay? And in this section and this section, if the force and the displacement are in the same direction, we have a positive work being done. In other words, that force is speeding it up. It's increasing the kinetic energy, as we see here, and thus it's decreasing the potential energy. Okay, so I'll grant that there's a lot of signs being thrown around here, but if you can remember the relationship between the directions and the sign for work, then you should be good to go. Okay, but this may take a couple iterations. This may take a little bit to mull over and think about it. Okay, but try and think about it in terms of energy and how that relates to the work being done. All right, thanks for watching.